This week we will be covering Producing Colors, which is Chapter 6 in the Bill Meyer book. This chapter deals with the industrial colorist and with the work that person does. Truly the person this program is designed to train, a person that is responsible for producing materials that are perceived as matching a physical sample submitted to them, or sometimes the verbal descriptions of a color effect stated by a designer or stylist. Generally speaking, when we're working in the plastic industry, we have some sort of physical sample that is sent in by a customer. It's the job of the color matcher or the industrial colorist to come up with a formula that matches that particular standard in color. Not only that, but also must be matched in the correct resin and also be able to work in the application that it's intended for. Also last as long as the customer would like it to last for, and of course it must all be done at a reasonable price. So not only is the industrial colorist worried about getting the right color, also that it has all the correct properties to work in the application that part will find its end use in. The key component for a colorist to match colors is an understanding of the relationship between the coloration process and the resulting color. For thousands of years, the skill to produce a particular color was developed through experience. And even in industry, colorists, up until at least the last 10 or 20 years maybe, relied on experience with using the colors in the process that they're working with to determine what the correct formula is and to produce the color that the customer wanted. Nowadays, the colorist has more tools to work with than has ever been available before. In the old days, the colorist learned through experience how colorants combine to produce different colors and how changes in the amount of each colorant produces changes in the final color. This was usually done, at least in the beginning, by trial and error and by working with an experienced person who helped the new people through apprenticeships learn the art and skill of matching colors. Nowadays, while experience is still very important for the colorist, there are many more scientific tools available to aid in the color matching process. So we have spectrophotometers, we have color software, we have systems that can read the color and tell us how far off it is, what direction it's off, if it's too chromatic or not chromatic enough. All of those different attributes or differences in all of those different attributes we've talked about throughout the course. There is some kind of model that is used for making colors, whether it was arrived at by experience or it uses a spectrophotometer and an instrument. It doesn't really matter how it is arrived at. Color model is developed that relates the inputs of the system, colorants in the colorist's palette, so whatever colors are available to the color matcher, and we relate that to the output or the desired color, the standard we're trying to match. Now, when the color matcher goes about matching a color, most of the time they don't come up with the exact color on their first attempt. It usually takes at least a few times or iterations to get the right color, and when we say the right color, that may not mean that it's exactly the same color of the standard, but it's within acceptable tolerances for that particular application. And that can change depending on things like who the customer is, what the final product is, and what industry that product goes into. The number of iterations or attempts is certainly related to the colorist's experience and ability. It is rare for the colorist to match the color on the first shot, but generally the better the color matcher is, the fewer shots or fewer attempts that it takes to get to the right color. For many coloration systems, the relationship between colorants and the final color is very complex. There's a lot of variables that are involved in it. So it's difficult and time-consuming to develop a model based on experience only. So to speed up the process, we need to get a little bit more scientific, find a better way of developing a model. Again, we've developed models throughout this course for color. The better the model is to the actual reality, the better the color matcher will be at getting the right color sooner. For instance, changes in raw materials such as colorants or resin increase the number of iterations needed. Ideally, if you have certain colors, those colors will always stay the same and they won't change, or you won't add new colorants to the system. That keeps it less complex, but in real life, colorants change. They shift a little bit from lot to lot. You may change suppliers for the same colorant, or you may get new colors as new colorants are developed. So it's a constantly changing system. So if you're only basing your results on experience, it gets to be kind of unwieldy and complicated. Mathematical models can be and have been developed to augment a model based on experience only. Just because a mathematical model is used doesn't mean that experienced colorist is no longer needed, but rather that the mathematical model can greatly improve the efficiency of the colorist. No matter how good the mathematical model is, or the system or the instrument is, the key ingredient that must always be there is the trained color matcher that can use the model, use the system, and use their experience to come up with the correct color quicker using all of the tools available. A good example of where a mathematical model would be an advantage would be when a new colorant is added or a colorant was replaced in the color palette. So now we're changing the set of colors that we can use to make up our final color. In most mathematical models, it is usually straightforward to replace or add colorants by changing the input data. We have a spectrophotometer and a color matching software that requires a certain amount of white letdowns and black letdowns and mass tones. The input into the system, we just make up those samples that are needed to characterize the new colorant, make them up, read them in, and the system can handle that new color. Colorists whose ability comes solely from experience would have to learn how the new colorants work. That means kind of a trial and error process where they'd have to actually use the colorant and most likely use it incorrectly until they figured out the properties of that color. The mathematical system could determine the characteristics of the new colorant and put that into the system right from the beginning. So we can look at several different kind of color mixing laws. A mathematical model can be developed by studying the chemistry and physics of a coloration process to discover the laws that govern the mixing behavior of the colorants, or we call that color mixing laws. There are several types of mixing laws that we will investigate. Those types of mixing laws are additive mixing, simple subtractive mixing, and complex subtractive mixing. We've talked about all of these at least a little bit early in the course. Now we'll look at them in a little bit more detail. The terms additive and subtractive mixing traditionally have been used to differentiate between the mixing of colored lights, additive mixing, and the mixing of colorants or pigments, which is considered subtractive mixing. It's whether you look at the way the final color is made by adding colors together, or by starting with all the colors and then subtracting some of the colors away, and the resulting color is what's left over. First, we'll talk about additive mixing. Again, this is the mixing law that applies to colored lights. And in additive mixing, we have three primaries. Those three primaries are red, green, and blue. Some of the applications where additive mixing are used are in theater lights. If you look up at the lights in a theater on stage, you'll see there's several banks of red, green, and blue lights. By changing the intensity of the different colors, we get different final colors that can be used to wash the stage. A disc colorimeter is also a device that uses additive mixing, and what it has basically is a disc with movable sections on it that can expose certain colors, and then by the amount of those colors that are exposed, when the disc turns at a high rate of speed, instead of seeing individual sections of different colors, it all to our eyes looks like they're mixed together, and you get a composite color. With our three primaries, red, green, and blue, when we add the three of them together, we end up with white light. So red plus green plus blue equals white. And if we look at that, and this is a picture that's out of your book, and if you look at your book, you'll probably see better colors than what we see on the screen here. But you can see in the center where all three of the lights are added together, we get white light. And if we look at the green and the red, we get yellow. If we look at the blue and the green, we get cyan. And if we look at the red and the blue, we get magenta. Later on, that those three colors that are produced with a combination of the additive primaries are the subtractive primaries. So they are related, the additive and subtractive primaries. They're kind of opposite. When we are talking about primaries or theoretical primaries, we recognize that the color names themselves as red, green, and blue are rather vague. We've talked about exact colors in the past in this course. We've talked about certain wavelengths of light which relate to a certain color. So the graph on the next slide shows the spectra from three different primaries that are all named blue. Clearly we can see that they're not the same. So we'll need to define what we mean exactly by red, green, and blue to better characterize the exact primaries. We can see from this curve here that we have different blues in different applications. We have a blue for the CRT screen, like you're looking at on your screen. We have printing, which is a different blue. And we also have textiles, which is a third blue. Now they all have a hump over on the left side of the spectrum between, say, 400 and about 500 nanometers, but obviously they're not all the same. When we talk about blue primary, what exactly are we talking about? To eliminate the ambiguity by defining primaries by their spectra based on theoretical grounds instead of just giving them a name. We'll talk about theoretical additive primaries and theoretical subtractive primaries. Those are a little bit more specific than just saying primaries. Theoretical additive primaries, we can start with the visible spectrum divided into thirds with divisions at 500 nanometers and 600 nanometers. We can say light below 500 nanometers is blue, and that's really from 400 to 500 nanometers. And light between 500 nanometers and 600 nanometers is green. And then finally, light above 600 nanometers is red. So the theoretical red, green, and blue additive primaries produce light only in the spectrum region corresponding to their color name. So then we can adjust the amount of a theoretical primary, and that results in a different amount of light, but the same spectral character. So it's just think of it as the intensity of the light is changing, but not the shape of the curve. Essentially, the square wave changes its height or its amplitude, but not its width. As the amount of the primary increases from 0 to 100%, light is added. So the higher the wave, the square wave is on the graph, the more light is produced of that particular color. Secondaries are produced by combining pairs of primaries. Like we saw in the picture earlier, red plus green gives us yellow, red plus blue gives us magenta, and blue plus green gives us cyan. If we add all three of them together, red plus blue plus green, we end up with white. We can show this graphically on the next slide. As we can see, we have our three primaries. We have our green primary on the top, the blue primary on the left corner, and the red primary on the right corner. If we add all three together, the red, the blue, and the green pointing towards the center, we have a straight line all the way across, so that gives us white. If we look at the green on the top and the red on the right side, we add those together and we see the curve for yellow. We take the red plus the blue, add those together, and we see it on the bottom, we get magenta. Finally, if we take the blue plus the green, add those together, we get the curve for cyan. So theoretically, that's how we get yellow, cyan, and magenta from red, green, and blue, and white from all three of them added together. So we can look at the way additive mixing works in another different way. Hopefully this will help explain it more fully. We can start with two white lights. They're made up of yellow, cyan, and magenta. Remember, those three colors added together will give us white. And we have red and green filters that are used to produce red and green light. The red is made up of yellow and magenta components, and the green is made up of yellow and cyan components. The red and the green add together to produce yellow. If we look at that kind of as a mathematical equation, we have yellow plus magenta plus cyan plus yellow is really our total added together. We can kind of subtract out the yellow plus magenta plus cyan, which equals white. So what we have left over is yellow. We can sort of say that the yellow plus magenta and cyan equaling white cancels out, so the leftover color is yellow. Here's a way of looking at that graphically. We start out with our white light, and we have two white lights here. We want to have red starting out with. We use a red filter, and the red filter filters out the cyan, so we have yellow and magenta left, which is what red is. On the right side, we have a green filter, so the green filter filters out the magenta, so we have the cyan and yellow left over. What we have with the two lights then, with the filters, our red and green filter, we have yellow, magenta, yellow, and cyan. So yellow plus magenta plus cyan equals white, with our leftover yellow, so the color that we see is yellow.